So welcome back. Where we left off last week, we were talking about the different aspects of malware, really an attempt to kind of categorize their intention and how they trigger. And it is kind of obvious in some sense that a malware can be triggered based on some logical condition. If that logical condition has to do with a certain amount of time before it triggers, then it's referred to as a time bomb. Otherwise, the term is just called a logic bomb. Really, you're just distinguishing between something that activates instantly or activates after some condition is met. And where we left off, we were talking about a couple scenarios in which intent really is what matters here, where a particular piece of software would trigger to shut down if it reached a certain geofence location, or a developer of these sort of intelligent spreadsheets determined after a certain period of time that they would need to be consulted again. So there was financial or other motivation for it. That is a type of logic bomb. I guess you could say if there's an if statement in your malware, then it's technically a logic bomb. But it can get a lot more complicated than that. So we've talked a little bit about Stuxnet before. We talked at the time how it was loaded via the physical security of a USB drive. But it was much more than that in terms of how it was triggered. It was a fairly advanced piece of malware, and it's still considered to be a fairly advanced piece of malware. It used 4 previously unknown Windows vulnerability. One of them was a USB vulnerability. Then there was a separate keyboard vulnerability for privilege escalation. There was another vulnerability with regards to how drivers were being loaded. But the logic bomb aspect of it was also very unique. Compared to the others that looked at a geographical location or waited for a certain period of time, this looked for not just any Windows computer that may itself be vulnerable, but looked for what was potentially attached to that particular Windows computer. If you don't remember what this was about, this was back in the news, I guess, these days. Iranian centrifuges attempting to enrich uranium. That's really all I know about the actual chemical engineering associated with that you have specialized devices with specialized control software associated with it. A company called Siemens used the control of these industrial devices, and that's what that malware was triggering on. If it was any old Windows computer and it wasn't connected to one of those devices, or at least what it was checking, if it had that particular piece of software loaded on the computer, it wouldn't do anything. It would just remain inert. It would just be a piece of software resident, probably not good to have on your computer, but it wasn't doing anything actively malicious. If it looked for and found that library associated with controlling those centrifuges, it then would start to activate. That would be the logical condition that it had there. The kind of thing it would do, and we can briefly look at the code for it. It's not that edifying, but it's just an example of maybe industrial strength malware. It would look at these centrifuges that were intended to spin up to a certain frequency range, and it would just mess with the oscillations of that range. So via low-level PLC, these programmable logic controller code, which is really just looks like binary blobs at the end of the day, it would periodically change the frequency at which they were spinning at. And again, we're in the right building for that today. I don't have true expertise in terms of why that particular oscillation between frequency ranges itself cause irreversible damage to it. But that was the intent, and it actually did work in practice, that by embedding, by very carefully not always just activating, but only activating when the particular conditions were being met. There was a separate command and control server associated with it, and then when it would actually be activated, it would do some periodic cycling of the frequency of it at such a range to cause the motor to physically burn out. Just think of it as kind of slamming on the gas and slamming on the brake of your car. That's the closest analogy I can think of. You do that enough time, you mess with your transmission or something along those lines, and that's what it did on those devices. So the trigger itself is also a logic bomb. Again, I have the source code. There's been various efforts to sort of reverse engineer the source code for it. Usually you can tell when the source code available, let's say on GitHub, is via sort of reverse engineered efforts versus something that was originally provided as source here. This one is definitely reverse engineered. They even talk about how successfully it was reversed or not. The link is there. You can also look at it yourself offline. We don't have to go through every line of this one. It is not that useful to look at, other than it's doing a lot of searching for a very particular library. It's looking for a particular set of function signatures in loaded libraries on the computer. And if it finds that, then it does activate. If we look at the rest of the code for it, though, it's still just basically assembly blobs here. And that's part of the nature of the kind of activity it was attempting to do, in that it's running this, it's trying to load this PLC code, and that itself is not something that's really human readable code, at least the version that we would care about. And it's just pushing a lot of binary blobs to the associated library and associated device. In this field, if you want to be able to reverse engineer malware, you do eventually have to get at least somewhat familiar with assembly code. Now, there's different levels of skill set associated with that, and there are, of course, the classes that you get to take. And certainly, if you're in cybersecurity engineering, you get to take the embedded systems class, you get to take the computer architecture class, but you definitely at least need to be at a place where you have some fluency in assembly, because oftentimes the type of thing you're looking to analyze isn't provided for you in this nice, clean GitHub repository. You're given a .exe file, and you have to figure out what was the intention behind this file. That's not to say that that's an easy task, and there exist other classes you get to take here. There's whole suites of tools specifically intended for that purpose. But at the very least for now, in terms of where you are in your academic careers today, you need to get to a point of basic fluency with what is happening in this code. It's not that interesting, so I don't want to go into it too much. This is just doing some very basic, just pointer handling, just modifying values here. I couldn't find, in looking at these various assembly block codes, anything all that interesting to say, well, here's where the real interesting malware here is. But you should be able to look at it and say, okay, I can kind of trace what it's doing here, pop a value off the stack, do a comparison, jump if those two values are equal, just doing some kind of jumping around in the code and copying values over. That is a version of Stuxnet. That code doesn't show the actual vulnerabilities that were used to stage it. That's just what was ultimately loaded on those computers, and that's the extent to which it's reverse engineered, at least in public fora today. We talked about how it's triggered. We also briefly talked about the different types of payload being relevant here. Again, malware, malicious software, it's doing something bad, something intended to be bad. You could argue that the simplest thing to do is just to break things, I guess. So when we talk about either system corruption or data corruption, it could just be as simple as, can I take this machine down? Can I do something that causes this machine to no longer act as effectively as intended, or just to have to kind of reboot or have other problems here? That's separate from information theft, although you could have malware that attempts to do both, and we'll talk about a couple of different examples there. And then I want to talk a little bit more about rootkits and what that means, how to establish persistence beyond just having a reverse shell, which is a valid way to think about it, but can we do something that's a little bit more covert than that? In terms of system and data corruption, a very early and influential example is the so-called Jerusalem virus and the many variants here. Its intention was just to, every time it was executed, it would then add some just garbage bytes to every executable file, which doesn't sound that bad, but the idea being that you wouldn't notice that you were infected at first, and then over a sufficient period of time, as your computer is just executing its expected and periodic tasks, eventually you would run out of space and cause things to kind of crash. It was also unique. It was also a time bomb to delete executables on Friday the 13th. I thought that was sufficiently interesting to show. This one's entirely in assembly, but again, fluency in assembly is probably a sufficient goal for you, at least certainly by the time you graduate, if not today. There isn't that much that is going on here. It is doing basically a system call to do an interrupt, grab the system time is what that's doing, and then it's literally just comparing the year information. If it's 1987, don't do anything. So this is dated, but you could update that for current days. Compare the day information. If it's Friday, continue. Compare the actual date information. That's a little hard to read. That's 0D hex, so that's 13. So if it's a Friday, if it's the 13th, go to that other payload part of the code. So that is also a time bomb, right? Checking if the date is Friday the 13th, and then do that type of executable. This is influential because it's a very early example of having done that. Not that it's necessarily that difficult to detect and define things here. There's also this concept of ransomware, which is something that we currently face quite a bit more on a day-to-day basis. Idea of ransom is you're holding something hostage and requesting money or other things in order to release your hostage. Ransomware is software that is itself performing some sort of ransoming. Typically, it's also going to involve the things we're going to talk about with regards to rootkits so that it's not easy to remove. And at least today, typically what a piece of ransomware is doing is some version of full disk encryption or database encryption, which can be a good thing if you yourself are the one doing the disk encryption and you are responsible for that secure storage. But if it's some other unintended piece of software doing that for you, that's generally not what you would want. So the idea is you have this malware, it gets loaded via whatever mechanism, it gets triggered also then via whatever mechanism that like we talked about, and then the actual payload is to do some background encryption of your database or critical files of your entire disk. The idea being the ransom is, pay us money, or we will never give you the key for it, and you have to kind of rebuild from scratch. That seems like a straightforward trade-off to make, but I think it's never necessarily that easy to consider. If you assume, we have just perfect offsite backups for everything we do, and so if you encrypt our disk, we just unplug all those machines and restore from offsite backup. In theory, that kind of thing can work, but in practice, what happens is the organizations that get impacted by things like ransomware, they have some security posture, but they're maybe not that advanced, maybe until they have faced such an attack. And if we just limit our search to just Des Moines and limit our search to Des Moines in, say, the past 4 years, it's just been ransomware attack after ransomware attack. So those of you who are local to central Iowa may or may not have been familiar with it. And I just linked to a number of news articles on the various ransomware attack. I had the link here somewhere. So Mercy One, so the major medical system in central Iowa, they were hit with a ransomware attack here. Depending on what systems were attacked, it can take a very short period of time, or it can take a very long period of time to recover from that. Another one that had happened, and there's many, DMAC, and maybe some of you were at DMAC or taking classes through DMAC, had all of their sort of student information systems completely taken down by this, and it took them a couple of months to recover from this. This was not a quick recovery for them. This one impacted my family directly, where Des Moines Public Schools also had a ransomware attack, so we had to delay our vacation because the school year got extended. Don't cry for me. It was okay. We still had a wonderful vacation. But what's interesting about that is it's all very similar type of scenarios. There's a vulnerability, there's a trigger. The payload itself is proven to be a very destructive one, in which it's one thing just to take a computer offline. It's another thing to kind of encrypt the entire database that's of interest so that you yourself can no longer use it. I have read articles, I don't know the true underlying facts of to what extent this is an effective thing, that some organizations are starting to buy things like cybersecurity insurance as part of their posture, as part of their certification of various standards. It's not that clear to me how effective that is at the end of the day. Sure, you get some payout, but it doesn't magically fix the cybersecurity issues you are having. Your systems are still offline. Maybe financially you're not taking as large of a hit, but then I assume there's a further legal process associated with that. Another notable recent example is the Colonial Pipeline ransomware attack that just started with a singular breached employee password, and that was a major U.S. Gas pipeline, and they did pay a 75 Bitcoin ransom, which at the time was like $4.4 million, and it's a decent amount more even today. Since then, at least the article that's linked there, it was mostly recovered by the DOJ. I think how they would do that. The whole point of Bitcoin, to the extent you're familiar with it, is supposed to be kind of anonymous and decentralized. How do they recover Bitcoin? Any idea how they would do that? Department of Justice, this company paid the ransom, but it's not that clear. You can read 100 articles and not know for certain whether or not Des Moines Public Schools paid the ransom or not. It's really not clear. And reading between the lines, I think they did, but I cannot prove. I have no guarantee. I don't have enough knowledge to know for certain whether they paid it. This one was publicly released that they paid it, but they got at least some of it back. How would the Department of Justice or anyone really recover a Bitcoin that's been paid out? Yeah, well, in theory, you could just someone had to have the wallet to provide that payment in the first place. There are all sorts of services that look to kind of scramble wallets after the fact. So that payment happens, you then try to scatter it to the wind. But presumably these attackers, they actually wanted the money. They wanted to be able to use it. So assuming there could then be separate legal proceedings against them, you can probably force them to give up their key afterwards.
So I looked up
the Colonial Pipeline.
Pipeline, and it says that they kind of split the transactions at about 63.7 Bitcoin was transferred to a wallet the FBI could access, though the exact method of obtaining the private key remains undisclosed. So they did obtain the Bitcoin back through legitimate means as far as Bitcoin, but I don't know if they fished them for the password or if they somehow got somebody to tell them the password, or just used like the monkey wrench method from the XKC.
Right. So that's a good point. So when we talk about this being an anonymous way of doing payments, it kind of sort of is. It kind of sort of isn't. I guess once you get to the multi-million-dollar kind of payments, it can stop being anonymous at that point because there's sufficient incentive to be able to track the payment as it happens. I think in this case, it was the Department of Justice. There was some sort of arrest and legal proceedings, and as part of that, someone can be compelled to give up that information. Or if it's stored in a cold wallet, as they say, it's on a USB stick somewhere, then if you can get access to that, you can have it there. These other ones, though, this was a pretty public case. That's why I listed it here. These other ones, it's not clear. Did they also pay the ransom, or did they just rebuild from scratch? The DMAC one was a period of months that they were still offline, and we all had to go back to paper and pencils and not have any access to grades or things of that nature. The one in public schools also was quite impactful in terms of people's graduation, being able to get transcripts to send to colleges. It was very destructive at the time. Separate from just being sort of a destructive action or a sort of disk encryption action is the idea of just information theft. So the malware is just gathering data, and that is what's considered valuable, not the potential money gained from just getting a ransom, but the actual value of potential information here. So things like username and password and credentials for banking or gaming or other just general system. If you can impersonate an important user who has access to a lot of money, then that would be a valuable goal of that malware. One famous example is the so-called dark hotel group. That's kind of a westernized name for what they are. It was in South Korea. The idea is they were targeting executives of important companies through business hotel Wi-Fi networks. That's why they were called dark hotel. The idea is that you would connect to the Wi-Fi. It was actually sort of a malicious and impersonated Wi-Fi, and they would use that to then steal credential information. A little bit more, vague in terms of what particular information and what it was being used for, but that was the purpose of that kind of hacking group, that they would then be able to impersonate legitimate business users for future purposes. Another mechanism and a channel for information theft is to use a keylogger. So historically, a keylogger was a physical thing, and it still can be, but we can also think of it as just being a piece of software as well that's actually capturing the keystrokes on an infected machine. So assuming you have just kind of a raw log, that could include useful information, or you can set filters to just check for usernames and passwords that are getting typed in. For research purposes only, very similar to the rubber ducky that we were playing with. I'm also tempted to grab one of these, but it's a very similar thing to the USB cable we were playing with. You plug it in, assuming it's on the back of the device. You don't notice that your keyboard is now plugged into that versus directly into the port. You could probably even be smaller form factor than this one, because this one is a Wi-Fi access point and is just trying to kind of broadcast information for research purposes only, but it's a piece of software that could also do that as well. So, right, your keyboard is a physical thing. It's interacting with your operating system to deliver keystrokes to the intended application. If you have a piece of software sitting in between that connection between physical keyboard and operating system, you can then capture keystrokes and grab what other information could potentially be leaked through that. That, falls into a more general category of just what's referred to as spyware. It's somewhat of a similar concept. So a keylogger specifically for keystrokes. I'm typing something in and that's what's getting captured. Spyware is just a general term. It's referring to anything that's sitting as sort of a man in the middle and potentially capturing information in a bidirectional manner. So a keylogger is a type of spyware, but not all spyware is keyloggers there. It's very common when we were talking about web application security that part of setting up a man in the middle is to kind of capture login information on a malicious but seemingly correct looking website. But there's various other aspects of that information flow as we access network capable applications and services for which a man in the middle, a person in the middle, a piece of malicious software in the middle can be sitting. One somewhat notorious example is the Pegasus spyware, and that's the NSO group. I refrain from political things in this class, although this topic can get somewhat political. I found the website interesting, though. This is not a political statement, just an observation. The NSO group. I look at their website. It looks pretty good. I don't know. It looks cyber intelligence and global security and stability. This looks like a company I'd like to go work for. NSO creates technology that helps government agencies prevent and investigate terrorism and crime to solve thousands of lives around the globe. So they got that nice flashy website. Not only that, they're very open about like what jobs are available. I know some of you are looking for jobs, and I'm not saying you but hey, security researcher sounds pretty good. Be part of the OPSEC department, which is in charge of research, design, development, and enforcement of advanced OPSEC solutions. Okay. Well, what about tech? In-depth knowledge of Android OS internals. You may not have that yet. We have that CPRE 3880. You'll learn more if you take that class. At least 2 years of experience, so this might not be your first job, but maybe after your first job. Malware research, mobile forensics, vulnerability. Tools such as Frida, JADIX, JEB, or similar tools. So if you take the reverse engineering class, you'll get a little bit of that. Evasion and anti-reverse engineering. Software development skills in Java, C, C++, and Python. BSc, so a Bachelor's of Science in a technological field. Ability to work independently and as part of a team, and they definitely want an Android and development experience and experience with things like Wireshark. You have that now. You know, we didn't really do Burp Suite at all. We could have in this class, but we didn't. But Wireshark, you have some experience as well. You should consider applying. This is a company or an organization that is also on the, if you go work for them, you may not be allowed back into the country. So that was their website. It is a very nice website. They have lots of jobs available. This is an Israeli cyber intelligence firm, and that's what they're known for, is that spyware Pegasus, which has been used for surveillance of dissidents and journalists and maybe bad people too. I don't know entirely all that it's being used for, but their software, which a lot of it was running on Apple systems, was meant to be this kind of silent and resident software that was just slowly and quietly just tracking WhatsApp and other messages, iMessages being sent on that device. And that's still what they are known for here. But if you read the Wikipedia article, you'll find that they are now considered non grata in the US. And you probably shouldn't. This is my only political, you probably shouldn't go work for that company unless that is your life's ambition. Now, if you work for the equivalent organization, either directly or indirectly funded by the NSA, if you go work for Palantir, maybe it's very similar type of skill set. But that's an example of a spyware for mobile development. You notice what they were looking for in that careers page there. They're looking for the Android equivalent and to work on that team. They are using those previously unknown vulnerabilities to establish persistence on devices and in such a way that could intercept legitimate traffic on those while maintaining as much stealthiness as possible. When we talk about covert access, of which that spyware would certainly be an example for it, the idea is that you have some entry point into the system that is not easily detected. And as we'll talk about, this is not a binary thing. It's not stealthy or not stealthy. It's always a matter of degree to what extent the malware that you are inserting is something that can be easily detected, to what degree by some other monitoring or other piece of software associated with it. There's two aspects of that. First could be also still just the logical conditions. What is the triggering to actually enable it as part of it? But the other aspect is how it's actually built into the system. What is the access mechanism for that system? So when you read things about something being a backdoor or a trapdoor into a piece of software, that's what we're starting to talk about. Our reverse shell is the most kind of hard hammer approach to that, where we are explicitly just hosting remote access to this computer. That's really not intended to be necessarily a stealthy mechanism here. but there are all sorts of other stealthy mechanisms that allow one to obtain and maintain that sort of covert access into this. I was maybe feeling a little silly when I put this together. You'll hear the term backdoor and trapdoor used interchangeably, but at least on The Simpsons, those refer to two different things. Trapdoor goes straight down. Backdoor is very easy, legitimate access. But I may be dating myself with this bottom one here. Very difficult, legitimate access. Several layers of security they have to go through to be able to access this, to get to the secure room. And then there's the back door. It's just a ramshackle screen door there. So this one is a trapdoor, which I don't think was being the appropriate analogy. This is the back door. There's the intended difficult way to access the system, and then there's the easily maintained way of getting illegitimate access to the system. When we talk about covert access and maintaining persistence, a big part of that, and the terminology you will hear, is a so-called rootkit, which is a kind of dated term that people are still using. The idea is it's whatever piece of software that is installed on the system, maliciously, and the intention is usually, is to provide that level of root privilege. So it's called a rootkit. It is a kit, a collection of software, a module, a piece of software that allows one to maintain that root privilege. It's not a very useful term just as literally interpreted. What it also usually then refers to is a piece of software that may provide that root access, but is really, it's meant to be clever in terms of how it's hiding how the intrusion happened and hide any sort of evidence that there was intrusion. So you'll have to just kind of make that mapping in your own head to remember this. When we refer to something as a rootkit, that's actually generally what we're referring to, not root user, although that could be also it, but also software that has some mechanism to kind of trick the supporting software into not being aware that it exists. So there's a level of interaction that really depends on how it is installed and what level of historic rootkits, if we're talking very early days. The idea is that you would just modify user space programs, regular applications, to just not be aware of the presence of this particular piece of software. We talked about that briefly when we brought up this general topic of malware, that reflections on trusting trust software, which, if you recall, what they did was they changed the compiler to, when it detected that it was compiling the login application, to instead compile a slightly different version of that login application. It was two levels of change there. That was effectively an early example of a rootkit. What it was changing is the actual utility program, the login command, the login program, and changing that one so that it would both take the expected password, the normal password, as well as some hard-coded extra backdoor or trapdoor password associated with it. That's what was interesting about that is because it was done at the compiler level and not just modifying the source code itself or the binary itself for that to make it harder to detect. So historically, that's what these rootkits were. You would change certain important utility programs to just basically not be aware of the presence of something malicious. So for example, if we are familiar with the ls command, list files in a given directory, you would have it act as the regular ls command, except for if it's looking for a particular malicious directory or piece of software, that program would be hard-coded in some mechanism then to not return that result. Right, if we think about that, and it goes back to that trusting trust paper, we very much trust those utilities to accurately reflect the state of our system. The other command is ps, list all the processes running on the system. There's an inherent level of trust we have in that program, that when I type in ps, it's going to return, or task manager in Windows, it's going to return all the applications that are currently, all the threads that are currently running on that system. But that was a piece of software written by someone to actually loop through all the different IDs and actually return all that information. It's a piece of code like anything else. Well, if someone has a piece of malware, that becomes a very nice target, right? I'm going to modify those programs, for instance, to otherwise act as they're supposed to. If it just completely broke, that wouldn't be very stealthy, but to do everything it's supposed to, except for when we get to this particular process name, don't show that one in the list. Just happen to skip over that. We'll look at what that looks like from a source code perspective. That was kind of a user space version, which is just overwrite the ps command. Well, nowadays in a modern system, you can't just overwrite those commands, or it can be detected that those commands have been changed. And so now oftentimes you'll have the rootkit where it's acting by inserting something into the operating system itself. That is a bit of an arms race. So the kernel, the operating system kernel, can detect that those user space changes have happened. So now an intention of a typical rootkit is to change things at the operating system itself. Well, you could have a VM that's running that should be able to detect when operating systems themselves have been changed. So now you would have something that would have to happen at the hypervisor level. And you sometimes see the term hyperjacking, but it's really the same concept. We are getting one step below the monitoring software and hiding the presence of something potentially malicious here. That is the concept of a rootkit. It is related to the concept of obtaining root in a system, but it's much more than that. Really, the thought is we're hiding the activity of something else malicious happening in the system. I want to use Wireshark to detect whether or not my software is pinging random websites that it shouldn't be and accessing data that it shouldn't be. That involves a level of trust in that application, right? You are trusting that application is actually capturing all of your network traffic. First task of a rootkit should then be, if I want to hide the presence of this particular traffic happening, just modify that software or tell it not to return results associated with this range of IP addresses. It's not a foolproof thing. It's not something that one can't overcome. You could have separate physical networking hardware that would be detecting these things. The LED is flashing or not, or there's other things one can do, but it's a way to kind of maintain that sort of stealthy persistence here. And again, it's a bit of an arms race. You could start by just modifying just applications. If that's something that's detected by the operating system, the next step would then be modify the operating system itself. And if that could be detected, the next step would be to modify the hypervisor and go one step below where the current level of monitoring is taking place. And that's the concept of a rootkit. A pretty famous example, I'm dating myself here, but we used to go to the store and purchase CDs to listen to music. It was very antiquated. We spent a lot of time in those CD stores and tape stores before that. I'm not old enough for record stores, but same concept here. And Sony was very concerned about people in this era sort of ripping the CDs, grabbing the audio information off the CDs to be able to then store it locally, to be able to share it with other people. Back then, the thought is if you bought that CD, it was only for you and you couldn't share it with a friend, or if you could, you had to manually give it to a friend. You couldn't electronically share it with a friend. And there was a period of time where they decided we want to prevent that from happening. So what the CD would do would be a regular audio CD, but also you could have hybrid CDs that were both audio and also had executable code, binary data on it, and they would detect if it was inserted into a Windows machine and would install effectively a rootkit. They didn't use the term. The idea is we're inserting some digital rights management code to just prevent you from doing ripping of the CD to MP3 files so that you can share on LimeWire and Napster and places like that. But it effectively was a rootkit. So that was for a period of time that you'd buy a CD from Sony, which was one of the major distributors of music, and it would actually be installing an anti-piracy rootkit on users' computers who played their music CDs. There's a rootkit source called diamorphine that's pretty easy to read, and so I thought I would bring up that example of what does a rootkit look like in practice. Again, the point of the rootkit is to hide that something exists on your system. That is separate from what the potential payload of the malware is. So whatever malware we want to hide is doing something bad. I don't know, it's encrypting the disk, it's leaking information, it's doing something that wasn't intended. And the rootkit is maybe associated with a piece of malware, and its job is to hide itself, to not make it obvious that there is something unintended running on your software. So again, to the extent you're going to be able to look at this code and instantly get what it's doing, I don't know, it depends on your background. I think this code is not the kind of thing you would do in like a CPRE 3080 or a ComSci 3520 operating systems class. You don't do exactly this, but it's not so far apart either. So low-level C code that its intention is, how do I hook into a system, in this case a Linux operating system, to hide that something else is happening in my code? I'm going to try to walk through a little bit of this If you get it instantly, that's great. If you look at this and it's still a little bit fuzzy, that's okay too. It's really about awareness of what does this code even look like in practice. And this is one that's written for readability and understandability versus some of those other examples that have to be reverse engineered and are not very readable or understandable at all. Part of understanding a Linux rootkit is to understand a little bit more about how Linux operating system works. That's itself a whole other class. But what's really important to understand is the Linux operating system, at the end of the day, is just a wrapper over a large series of so-called system calls. Kernel do this, kernel do that, kernel do this other thing. And every application you've actually ever run, probably written in user space with C programming or anything in the Linux-based environment, is ultimately just wrappers around those kind of things. Those are not meant for user space applications, so we build the C standard library or Python's built-in functions or Java's way of doing things. At the end of the day, it's calling one or many of those system calls. Once you know that, that's pretty much all you need to know about how Linux works. The source code for those calls are pretty painful at the end of the day. You're not the intended audience of those code. So for example, and this example doesn't look all that good, but if I want to open a file, in C, I'm probably calling a function called fopen if I'm using the C standard library. Has anyone called fopen before in their lives? Okay. Fopen is a very light wrapper around the Linux system call number 2. That is the open call. And you can then look and see the documentation for what the header is for that open call. And the source code for it is open, and it does exactly what you think, but that is doing those low-level things of, okay, I call fopen. How does it actually know to open a file? How does it know to actually grab access to a file? How is it really, truly reading the bytes that are ultimately stored on a disk, interfacing with some driver associated with whatever hard drive is installed on this particular machine? Why does it work on this machine and then also my friend's machine, even though they're totally different machines? That's system calls. That's the Linux philosophy. You have a driver for the hardware, you have a hardware abstraction, and you access those via all of these system calls. So we'll start with that if you can modify any of these system calls, you have kind of full control over the resulting system. So if you look at what this code is doing for this diamorphine rootkit here, it's basically just trying to find where are those system calls currently physically located, and there's functions to look up the symbol table and where it's actually the binary values are located in memory, and let's just overwrite a few of those system calls. This one, as just really more a proof of concept than anything else, is grabbing I like to call it get dense. I don't know if that's how it's supposed to be pronounced. Get directory entries is what that stands for, and the system call for kill, so to kill a process. Maybe you can see where this is going with right here. If I can overwrite the function or the system call to give me directory entries, if I can also overwrite the system call that allows me to kill a process, I now have some other piece of malicious software that's going to be much harder to find, and it's going to be much harder to kill. Again, we think of killing a process, we type in PS, we see all the processes that are available for us to kill. We type in kill, we type in the number or whatever the ID of the process, we then can kill that process. That is all under the assumption that those functions are doing what they're intended to do. So what is this rootkit ultimately doing? It's trying to find those functions. I don't know, it's just a lookup call to find it. It's then just going to overwrite those functions with its own versions of those functions. So this call, give me the physical table, where are all these functions located? Gives me the location of all those functions. Somewhere it's going to then overwrite that function. So for example, it's a little hard to read because it tends to be somewhat kind of sort of portable across different versions of Linux and supporting different microarchitectures. You could probably build a much cleaner version of this that isn't intended to be portable, but it's going to take that initial get dense call, which it should be in here somewhere. Get dense, there it is. Get dense, get directory entries, and it does exactly what you would expect. So for your C library, give me the entries of a particular directory. When you type your ls command, that's ultimately at the end of the day, it's calling that function to grab the location, the values of files and file names and file informations in a directory. And what this rootkit is then going to do is it's not changing the ls command, That would be a user level rootkit. This is going to be then a kernel module that is going to modify the syscall table that every time any code calls get dense 64, it is instead going to call this version that is compiled and installed at the time of loading of this rootkit. It's a little hard to see what it's doing here. We have our function declaration here. We have the results that are returned when we call the original intended Git directory entries file. And you have to keep scrolling down to see what's happening here. Grab all those values. Somewhere it should be hiding. If at some point we detect this magic prefix, there's a lot going on with this logical statements here. If the name length is greater than the string length of this, and memory comparison. So it's doing some sort of comparison of, is this magic prefix found in my file name or directory name here, then just get rid of it. ls command returns everything but whatever it happens to match that string, which I assume you could then change, but it's defined here as anything that starts with the name diamorphine_secret, then would just not be returned by anything that's calling that particular system call. And if we were to find the, what was it called? It would be hacked like kill function here. Here is the definition for it, but where's the actual implementation of it? I might have clicked into a different file here. If I go back here, here's our definition of hacked kill. It's going to do something pretty similar. It's going to check all the various returned processes that come through, and it's going to create its own version that determines whether or not a process is hidden or not. And that's its own flag that you get to then tag. Here's a particular process that I am declaring as hidden. It's still running on the CPU. It still exists. It's still resident on the computer. But ultimately, at the end of the day, we are trusting our user space applications, which are then trusting our underlying operating system, which is based off those system calls that do these most basic functionality of this would be the kill or the PS, but it's got another name for it to grab the current processes that are available on a system. That level of trust then, as long as we modify that lowest level piece of software running on our system, that's our rootkit concept. It does everything you would expect it to do, but we've just added a little bit of logic that says, well, except for these processes or except for these files, feel free to look at all those things except for those few here. I want to talk a little bit about command and control, but I'm going to leave that for Thursday. Thursday, we have our last micro quiz of the semester. I think I'm going to do it the last 10 minutes of Thursday, so I'm sorry for those of you who are kind of quick leavers. So come back on Thursday, stay for the entire Thursday. We'll have our last micro quiz of the semester. Looking forward to it. I know you are as well. Thanks.